All right, let's get started. Okay, almost spring break, so assignments coming due. PSA will be out soon, maybe not tomorrow, but soonish, so that it's not due for 2 weeks from today, so that'll be okay. How are things going on PS7? Okay. All right, I'll give you two. Yeah. No. Are you clapping for me or for the guy that asked the question? Yeah. Okay, so I mean it's possible because there's not because we got flexibility because of spring break. So yeah, I'll extend the deadline 2 days, and but the quid pro quo is that you got to understand when I don't read Piazza over spring break. So I'm gonna take a break from Piazza. So.
See, the next assignment's due like next Friday during spring break. So that's the trade-off.
Yeah, I won't do that to you. Any questions or problems I could help you with? Yeah.
So for the arrow keys event, since the spreadsheet panel doesn't actually receive any events from like the view,
yeah.
Do we have to, in order to get the set selection for the arrow keys, do we have to set a key event inside a spreadsheet panel so we actually have to go into the spreadsheet?
Yeah. So he's asking about arrow keys, dealing with the arrow keys in the view. So yeah, you'd have to handle events in the view. I wouldn't think the controller needs to know if the arrow keys have been pressed.
Yeah.
It might generate an event that says.
No, do we have to make an event inside of the spreadsheet panel? Because like I felt uncomfortable editing panel at all.
Oh, I've heard that you might have to modify spreadsheet panel to get the arrow keys to work right.
Okay.
And I've gotten questions about it.
Is there any other way?
Well, those of you that got the arrow keys to work, did you do it without modifying spreadsheet panel? Okay. Yeah, I keep promising people I'll look at it and post something, so maybe I'll actually do that tomorrow.
No, we have to actually
help you out. Yeah.
Is there any way to scroll automatically when you're selecting a cell that is like on the edge of the panel?
So how are you selecting?
So you're moving the arrow keys, and as soon as you get to the edge, you want to scroll to see further.
You're like A1 and go left.
Yeah, I'm sure there must be. I don't know exactly how to do it.
I'm thinking that I would have to modify spreadsheet panel in order to do that.
Yeah. No, you have the code for spreadsheet panel, so.
So we can modify it.
Oh yeah, modify it. I heard from one group that couldn't get it to show up in their toolbox, so they just they're writing their own.
Yeah.
I don't encourage that. Yeah.
I had the toolbox problem actually, and what I had to do was completely remove the project and then add it back in, and then add all the references.
So you had to remove the spreadsheet panel project, and then add it back in?
Yeah.
And redo the references. Okay. So that's good to know. Yeah?
If we have a pop-up block, we have a pop-up box for like saving, or not saving, but for like board block.
Yeah.
Should the controller know about that box, or should only the user know about that box?
Okay. So let's keep it will required. The question was, someone clicks on open file. Does the controller need to get involved with bringing up the file browser thing? I think. Is that what you're asking?
Not the. It was like the one like, would you like to say like if it's been changed? It was the box. Yeah.
Yeah. Well, the controller has to be involved with that decision to bring up that warning box because it has to ask the model if anything has changed. So yeah, I would think the controller would have to tell the view to bring the box up. Yeah?
For the help/information feature, should we bring up like a text file or like a dialog box that says like send dialog box that says like this is.
Yeah, just something simple, just a pop-up window with just a text view in it. Just so the TAs can figure out your interface easily. Yeah?
And the class that contains run new, like I think in your example was the file analysis application context,
Mm-hmm.
can that reference or call a method that's in the controller?
Well, it should. I mean, what it has to call the constructor.
It has to call the constructor, but can it call another public method? Is that allowed?
It's kind of, what method would you want to call?
For the purposes of opening a file that's already been populated, like,
Well, you would just pass that to the constructor.
right, but then how do you?
Oh, I see. Okay, you're clicking new. Maybe, let me talk to you about that later. I'm having a hard time thinking. Any other questions? Okay. All right, so what we're going to do today is kind of out of the normal flow of things. I want to talk some more about concurrency and synchronization. And as I mentioned last time, PS8 is going to involve, we'll be basically involved with this. So this is setting up for PS8. Once we get past PS8, we'll be back into a multi-assignment project you'll be doing. Hopefully PS8 will be not as time consuming as the others. So, we looked a little bit at locking, but not much yet, as a way of dealing with multitask. So we saw that we can have multiple tasks running at a time, but that they can interfere with each other, and there has to be some form of synchronization between them, and the only thing really looked at was locking. Well, these are, you might wonder, how important is it to understand concurrency? And so to help answer that, I put up 3 examples, and you can probably think of others, of where concurrency happens in real systems. So how is a web server, why is a web server on a list of things that have to deal with concurrency? Yeah?
You would have to spool up multiple instances of individual web app, possibly.
Okay, so a web server's sitting there, and it's just getting requests all the time. So requests are coming over the network, and it's dealing with all these requests simultaneously. And to make it perform well, you don't want it to be singly threaded so that it gets a request, deals with it gets another request, deals with it, makes all the requests wait. It has to be multi-threaded so that multiple requests can be dealt with at the same time. And if those requests interfere with each other, you've got a concurrency problem. Databases are the same way. A database system, and we'll be making use of one in a few weeks, can have simultaneous requests for the same data, simultaneous requests to change the same data. And so there's been a lot of research into databases to figure out ways to avoid that from causing utter chaos. Operating systems obviously have to deal with multiple things going on at the same time. Computers are multi-core. So these are examples of really high-level concurrency. What we're going to look at today are low-level examples of concurrency, the sort of the primitives that are used to build higher-level solutions. And the way we're going to do it is just by looking at some example code. And so I'm going to keep referring back to this so I do things in the right order. But first we're going to look at an example to create a lock. Homemade lock, one that fails, but so here is my code. And you'll notice this is similar, or almost identical, to an example we saw a few weeks ago when we introduced tasks. I'm running an increment task right here, and I'm running a decrement task right there, and then I'm waiting for them to complete. And then I write out the final value of this number in. And you remember that example. Increment just goes in a loop and tries to increment in, 100 million times, whatever the limit is. Decrement is trying to subtract. And we found that if we didn't use any kind of concurrency control, and we just had one loop that was madly incrementing in, and another loop that was madly decrementing, what happened? What went wrong?
They would equal each other.
Yeah. Yeah.
They both increment and decrement the same private variable.
Right. They're both banging on the same variable. But the problem was that n plus plus and that n minus minus are not atomic. They're not. An atomic operation is one that happens all at once, and it can't be interrupted while it's happening. Right? Another thread can't do something to n. In this case, say one thread is trying to increment in. If n plus plus were atomic, the thread that was doing n minus minus would not be able to interfere with the n plus plus. So we used locks to make it atomic. So what we did was we wrapped, here was this, n plus plus. We put a lock, well, this was the whole statement. We put a lock around that to prevent more than one thread at a time from executing the n plus plus and the n minus minus. So we did mutual exclusion that way. What I'm trying to do is do that locking example without using a lock. So let's see what I've done. I've got this Boolean variable up here called using n. And the idea is it's false, but when a task is about to modify n, it will set using n to true, and the other thread is supposed to notice that and wait until using n is set back to false. So here's my homemade lock. So each time I want to do an n plus plus, I have this loop. And notice there's no body of the loop. I got the semicolon here. So all this thing does is just spin while using n. So as long as that's true, meaning that n is busy, it's going to spin. Eventually, using n is going to get set back to false. At that point, it's our turn. We set using n to true, increment n, and set using n back to false. Meanwhile, down here, the same thing is happening. This thread is spinning, waiting for using n to become false, meaning it's not the lock has been released. Then we're going to set using n to true, do our decrement, and set it back to false. Okay? So suppose that the idea is if increment and decrement are running on different tasks, and suppose, say, one task gets here, and another task gets here slightly later, what's going to happen? What's going to happen up here? Since using n is initially false. Yeah?
On line 43, should that be decrement started?
That's a good idea. Okay? So suppose that this increment task gets to this while loop slightly before the decrement does. Yeah?
So decrement should be locked out because
Okay.
it turns using n to true.
So the idea is that increment will see using n as false. The loop will end. It'll set it to true. And then the decrement thread gets here and, using n has become true. And so it'll sit there testing using n until what happens? Until this task comes down here and sets using n back to false. And then this guy can start making progress. That's the plan. Unfortunately, as you know from the title of the project, it doesn't work.
On 51, you might want to change that to decrement.
All right. Yeah, we'll get to. Thank you.
That's breaking the program. It'll work now.
So what will happen?
Wait,
Yeah.
side note, I just had a question. What do the semicolons mean after a while?
That just says that the statement you're executing, is the empty statement. It's like doing this. Just having an empty body. And that's a mistake that students in 1410 make all the time. They'll write a while loop like this. They'll say while using n, and they'll do this, and then they'll put the body of their loop right here. And of course, they wonder why nothing, the body, why the program stops, basically. And it's kind of tricky.
Before me and my partner, like the last class, knew that you could do single line events like that, like while or for loops, like control flows like that, which is a single line after it. We had copied and pasted the the professor's code and put it in our project and started adding to it, and then we couldn't figure out why it was breaking because it didn't have the braces in it.
Yeah. Yeah, so I took a chance by doing this, but I want it to fit on one line, or on one screen. So this attempt to make a homemade lock fails. And it's possible to have both tasks executing in the respective critical sections at the same time. And you can see that. So if I run this, it ended with, a huge negative number in n. They were both increment and decrement the same number of times, so it should have been 0. So those locks are not locking very well. It's not like they're failing rarely even. They're failing like almost constantly. So what is the problem? Seem to make sense. One of them will set using n to true, and the other one will be locked out until the next one sets. Yeah?
Accessing using n.
Okay, he said accessing using n. So what is the issue? Yeah.
I was going to say, is the issue, like, what if they both hit the while at the same time, and it's both false, so it just goes to the next line, it's happening at the same time anyways.
Right. So if they're both executing this while at roughly the same time, they're going to look at using n, they both see it's false, so they both terminate their loops, and they both set using n to true. And now they're both inside. And that's what's called a race condition. There's sort of, they're racing to change using n to true. And the problem is, if the race is a tie, they both change using n to true, and they both get into the critical section. So fail. Yeah.
So wouldn't that mean that sometimes you get a Stack Overflow error from running the program? Like if both threads ran at the same time?
Well, we wouldn't get a Stack Overflow because...
Like they would both be stuck in the while. Oh, because it starts at a
Right, we're not calling methods. Yeah. Now, another objection you might have to this thing is, it's with locks, the threads block. They don't take up any resource. They just sit there until they're allowed to progress. Here, we're burning 2 threads with these busy loops. So we're using much more of the processor to do this.
We use events.
So, what's that?
We use events to
Well, he said, can we use events? We're going to see something a little bit lower level than that, but something similar. So the problem is that this here, these 2 uses of using n are not an atomic use. It's not all or nothing. It can be interfered with by other tasks. So we need to find a better approach. So before we look at the better approach, are there any questions I could answer about this? Sort of this failed attempt to do homemade locks. Yeah?
Would it be possible for it to deadlock if they access it at the same time as
Okay.
the bolts?
So is it possible to have a deadlock? So what would cause a deadlock would be if using n were true. Like if we set using n to true before at the top of the program, we'd have a deadlock immediately because both of these while loops would run forever because nothing to set it false. Is it possible to screw up so badly that both of these loops are waiting for using n to become false, and there's no way to ever get it set to false? What do you think? Is there a race condition that would cause that? I don't think there is, but I might be wrong. It's really tricky. Yeah.
Is using n a static value?
Yeah. Yeah.
So, because how static values are shared between classes and stuff. So when you start up multiple threads inside of a class, how is that value passed in? So they're making the same reference to that.
Yeah. The static variables are shared between tasks.
What if it wasn't static then?
Well, I could have, I just chose to, it was simpler to make all these methods static. I could have made them instant, just members and use instance variables. It wouldn't have made any difference.
Does it affect the thread differently?
No, not really. Yeah, I don't see a way this could, that sort of both loops could end with using n being true, because the last thing that happens is using n gets set to false. But I will also add that all these programs I'm going to show you are very simple code. And especially the ones I show you at the end, I don't do a lot of concurrent programming, and it took a lot of brain power to write these little programs. Usually programs of this length I can just dash off because I've been doing it so long. but it was like I was learning to program all over again when I wrote these. So it's hard to get this stuff right. Okay, let's look at one that works. So this is called working homemade lock example. And let's see what the difference is. Same setup. Now I have, instead of a Boolean, I have this number n up here, or I'm sorry, using n as an integer instead of a Boolean. And before anyone tells me, I obviously copied those wrong. So what has changed here? Yeah, so you see this mysterious looking method right there. Interlocked dot exchange. And that solves our problem. So let me explain how this works. What this does is it takes a reference to an integer, and then it sets the integer to 1. It sets using n to 1. But what it returns is the value that using n had before it was set to 1. And it does that atomically, so it's an atomic operation. It changes the value and tells you what the old value was. So normally that would take several operations. You do a store, you do a read to get the old value, you do a store to store the new value back. That'd be 2 operations, and they could be other operations could happen in between them from different tasks. But here, this happens atomically. So what I'm saying here is, okay, set using n to 1. So 0 means unused, 1 means being used. Set it to 1 and tell me what it was set to before. If it wasn't set to 0 before, keep trying. Okay? Now, how does this succeed where our old approach failed, that while approach? How does this eliminate that race condition? Yeah.
Can you explain how the interlocked again works? Maybe that'll give someone a hint to answer the question.
What? Interlocked? Right there?
That line basically working something all loop.
Well, this is the only new thing here. It's the interlocked exchange method.
Right.
So all exchange does is it takes a reference to a variable, like using n. It stores this 1 into that variable and returns the old value of the variable. So if using n contains 7, and we executed this, then it would change using n to 1, and it would tell you that the old value was 7. So but it does that as an atomic operation. So it happens all at once. Yeah.
So is it because before we were setting the using n and then checking it after, and that wasn't a complete atomic operation? Is that why it works here?
So before there were 2 lines. There was a while loop that was looking at using n, and then after it was a code that set using n to true. And those weren't atomic. So both threads could be executing their while loop, and then both threads could simultaneously be storing. Or one thread could execute the while loop, and another thread could come along and execute the while. Well, even after the while loop ended in the first thread, the next thread could come along, and its while loop could end. It could interfere. This is happening all at once. So let's take the race condition we identified and see how it's solved. What if both tasks hit that code and so that while loop and this while loop simultaneously? Okay? What's going to happen? Before, when they both hit it simultaneously, both while loops ended immediately because the using n was false, and then they both set using n to true, and we failed. Why can't that happen here? Yeah? Can you say a little louder? Okay. All right, so let's just think. So one task, this task up here is going to try to set using n to 1. And what is it going to be told was the old value? perhaps 0. This thread is going to do the same thing. So one of these threads is going to change using n to 1 and be told that the old value was 0. The other task is going to do the same thing and be told that the old value was 1. Because these two operations, this operation here and this operation here, are atomic. They can't occur simultaneously. One has to occur after the other. That's just a constraint that the implementation imposes. So even if they both try to execute interlock.exchange at the same time, one of them is going to go first and one's going to go later. They can't happen simultaneously. They can't overlap. So if this one sort of wins the race, it will set using n to 1. It'll find out the old value was 0, and it'll know that it was the one that changed using n from 0 to 1. And then it'll go ahead with the increment. And then it'll change using n back to 0. The other task is going to find out, it's going to set using n to 1, but it's going to find out that the old value was 1. So it's going to know, oh, it was already in use when I set it to 1, so I got to wait and try again. So it'll keep trying to do that until it finds out that it's the task that changed the value from 0 to 1. Yeah?
This interlocked.exchange,
Mm-hmm.
is that a method part of like this C# library? Or
It's a method from the .NET library.
Okay.
So system.threading, that namespace has a whole bunch of low-level primitives. And this is one of them. Yeah?
How do you know if a method is atomic or not?
You just have to read it. He asks, how do you know if the method's atomic or not? You just have to read the documentation. And if you go read, the Interlocked class provides a number of primitive operations that are guaranteed to be atomic. Okay? So before we were using a non-atomic combination we were testing a variable in a while loop and then setting it in an assignment that followed it. So the operations of those two statements are not atomic. Other threads can execute in between this statement and that statement. Here we're using atomic operation that solves our problem. Yeah?
What's going on inside these that makes them atomic, that blocks out everything else, so these two won't ever interact?
Okay. So he's asking what's going on, how is exchange implemented? Okay? We're going to look at implementing some low-level primitives, nothing that low level, but I can answer your question. I can suggest the answer to your question by this slide here. So I ran into Peter Jensen, and he asked what I was talking about today, and I told him. And he said, most of you are in 3810, and then I should mention this. So computers, their instruction set, there is typically at least one instruction that is a compound operation that allows you to build higher level atomic operations from it. So a lot of hardware has an operation very much like that exchange that we just saw. Now in MIPS, in the MIPS instruction set, there are two instructions that are there for atomicity. There's load linked word, that's LL, and there is store conditional, which is CC. And the way it works is, you use LL to read a word of memory into a register. Then you can do whatever you want to, and then when you're done doing what you wanted to, you use CC to store that register back to where it came from. And if any other thread has written to that memory location in between the LL and the CC, then the write fails and an error code is set. So these two operations provide you a way to create atomic sequences of assembly code. You start it with an LL and you end it with a CC, and it's guaranteed to be either that it was uninterrupted, nothing messed around with it, or it's going to fail. You can find out and try again. So operations like that exchange method are at some level implemented. It's implemented on hardware using instructions like this. Yeah.
And is lock something that doesn't go this far down but stays exclusively on the language?
Ultimately, lock would be, you don't talk about locks at the hardware level. You talk about atomic operations like these. But locks also, the implementation of locks in .NET would depend on instructions, in this case in the common intermediate language that .NET programs are compiled to. So hardware designers have to provide some source of, some way to do at least a couple operations as a single atomic operation. Okay, so we succeeded in building a homemade lock by making use of an atomic operation. Yeah?
If these locks, these pre-made locks that come with in the language are all located truly down in their assembly code language, is there no lock that you can truly implement in a high-level language? You have to reach for one that comes from a low level?
You have to, you've either got to make use of the low-level assembly code, that provides the atomic operation, or you got to build on top of some programming language artifact that uses it. Okay. Now, one problem with our homemade lock solution is it uses busy waiting, often called spin waiting. Right? When it's trying to acquire the lock, it's using up a thread with that while loop, a tight loop. It's possible to have threads communicate with each other, to signal each other. And this next thing, manual reset event demo will illustrate that. So let me get into it. So this is very simple. We have a main method that runs task1 method, and it runs task2 method, and it waits for them to finish. Also up here we have an object called a manual reset event. So I'll explain what that is in a second. But it's a synchronization, it's something you can use for synchronization. So task1 method, what it does is it says task1 is running, and it says task1 is waiting for MRE to be set, then it executes that code, then it says task1 is finished. Task2 says task2 is running, press enter to set the MRE, then it waits for you to enter an input line, then it calls MRE.set, and then it says task2 is finished. So the net effect when I run this, except I'm going to have to make this the startup project. So let's run it. So you can see task 1 is running, task 1 is waiting, task 2 is running, and now when I hit enter, both tasks end. So given all that, what do you make of, what do you think a manual reset event is? So we're using it there and we're using it there. It provides a way to communicate between tasks. So what do you think is going on? Yeah?
Would it be a static shared variable or object of sorts that once it says it's ready to go, then it will continue?
Okay, yeah, roughly. So it's an object. It provides these two methods. When you hit it, when a task, a thread gets down to MRE.wait1, we created the task up here. We created the reset event with false. So initially it's unset. It's in the false state. So when you hit right here, it is waiting for it to be set. So the task blocks until the MRE is set. And this method call here sets it. So we can arrange for this task to block until this task calls MRE.set, and that causes this block to disappear and this task to finish up. It's a way of sending a signal to another task. So it's a way of arranging for a task to block and then be able to cause another task to unblock it remotely. As opposed to, another way to do it would have been to have, right here, to have a busy loop waiting until a Boolean was set to true. But that would have burned up a core. So instead, we just block while we're waiting, and then instead of setting a Boolean to true, we just call the set method. That'll unblock the task that was waiting on it. So that's one way. That's a way to get rid of the spin loops. Yeah.
So why does the program wait for the read line, wait for you guys essentially? Why doesn't it just set back an empty string or something?
Well, that's just what console.readline does. It blocks until a line of input is available to be read. or until end of file is reached. That was just my way of, I had to have some way of controlling when MRE.set was called.
Yeah, it's like a read line, not read line.
Okay.
Well, like, you know, because
Yeah.
Isn't like when something, like for example, read line waits for the user to press enter when they type in text. Isn't it just under the hood? Wouldn't it just be using a loop to wait for the user to?
Well, you might be wondering, yeah, he's wondering, is this a busy wait right there?
Yeah.
I don't know. I kind of doubt it, but that's certainly not a busy wait right there. So even if read line's a busy wait, I've gotten rid of the busy waiting right there. Okay? So we're going to make use of that. It turns out to be useful to have one task be able to signal another. Okay. So we've seen that. So the next thing I want to talk about are read-write locks. And that's where we're going to make use of oh, I'm in the wrong place. We're going to look at read-write lock tests. We're going to look at a unit test to test reader-writer locks. But let's take a break first.
Sounds like Liam got a chance to look at the spreadsheet panel, is that right?
Okay, so I just noticed that my slides to tell me what order I was supposed to go in wrong. So anyway, we'll do what I promised later. This is another example, another low-level primitive that's provided by the Interlocked class. And this is, again, just our old example of incrementing and decrementing at the same time to see what happens. But I've removed all the locking, so you don't see any locks here, homemade or otherwise. But I've replaced the n++ with that call right there, and I've replaced the n-, with that call right there. And if we run this, you'll find out that it all ends up at 0. So what do you suppose that interlocked.increment and interlocked.decrement do? Yep.
Probably just increment and decrement that reference n.
Right, but they increment and decrement the reference variable, but there's an adjective we left out. Atomically. So n++ is 3 steps. And it's not atomic, and so threads can interfere. This guarantees to do it atomically. So before we were using locks to cause the n++ to be atomic. But this just does it for us. So there are a variety of methods in an increment class that take things that wouldn't be atomic and make them atomic. So sometimes that can simplify your job. You don't have to create locks. You just call the atomic method. Yeah?
What's the downside to this, to doing atomically? Otherwise, I guess we would use it a lot more.
Well, the downside, that gets back to a question on the midterm. The downside to using atomic operations when you don't need to is you sacrifice concurrency. So, plus, it's just more expensive. If you have a singly threaded program, there's no need to use an atomic decrement. n++ is just fine, or n-, is just fine. It's only when you have multi-threaded programs that you care. And if you might have a big critical section and in it do an n++. Okay, you wouldn't want to replace that with an interlocked increment because you already got things locked. No need to pay the price twice. All right, so just remember that we have an atomic way to increment and decrement. Now, the next one I need to show you is called monitor example. And this again is that same code. I'm doing the locking differently. What we did before, when we looked at this example a few weeks ago, what I did was this. I said lock, sync, n++. Okay? But now I'm doing something with this monitor.intersync and then it's try block. So let me explain what's going on. When you write this, the compiler turns it into this. Okay? So this way of writing things is just a more convenient way of writing this right here. Okay? So what happens is when you call intersync, you're acquiring a lock on that object. And then when you call monitor exit, you are releasing the lock on that object. That's all there is to it. Why might you want to use why might you want to use something like this instead of the simpler block right there? What would be the use case? Why not just always, if you're using a lock, why not use it that way instead of through a monitor? Yep.
Hash an exception.
Well, we could have put the lock into a try block. So it has nothing to do with exceptions. Okay. When is the lock released? The lock is acquired. When is it released? When we're using this form at the top here. Yeah?
At the end of the whole try block.
When we exit, well, there's no try block for this one up here. When we exit this block right here, there's always a block that follows the lock. So when we enter the block, when we exit the block is released. Sometimes you would like to be able to lock the method now, acquire the lock here, and maybe release it in a different method. And you can't do it that way. But you can do it with the monitor way. So it doesn't have to be written in this form. You could acquire the lock here, and then somewhere else in your program you could exit the lock, as long as that sync variable was available, the sync object was available in both places. So it just gives you more flexibility of when you can release the lock. Now, why did I put monitor? Why didn't I just say monitor.enterSync and then n++ and then monitor.exitSync? Why did I put monitor.exit in a finally block? Yeah.
Just to ensure that it gets released.
Right, to ensure that it gets executed. Now, it wouldn't matter in this case because we're not going to get an exception running n++. But in general, if you had a more complicated code here, it could throw an exception. The alternative is just, if we didn't have this set up right here, an exception would be thrown and this monitor.exit would never be executed. Putting it in the finally block, it guarantees that even if an exception occurs in the code that we have locked in the critical section, the lock will be released. So that's just good form. You got to think about this when you don't want a lock to not be released. All right, so we got monitors to play with. Okay, so now we can talk about reader and writer locks. So this is a sort of a standard kind of consideration in parallel programming. Suppose you have some resource and you got a bunch of threads. Some of the threads want to read the resource. Some of the threads want to write the resource, modify it. Now, one way to control access is to just have lock at the beginning and the end of each access, so that only one thread at a time can be reading and or writing. Can you think of a way to get more concurrency? While you're thinking, let me just show you. So what I've got here is a main method. It creates a list and adds a number to it. Limit's just a variable up there. Then it enters this loop and it adds a task that calls a display method, a task that calls a display method, a task that calls an insert method. So display just prints out the list. So it's a reader. Insert adds to the beginning and end of the list. So it's a writer. And then we start all the tasks, wait for them to finish, and write out the final form of the list. So let's look at the first version of display. We're going to do a random delay just so that the threads get sort of mixed up. The order in which they run gets mixed up. So it's a random delay get executed. Then we lock sync with a monitor. Then down here we print out that we are reading. We delay. Then we, actually I commented out the part that actually writes out the list. Let me put that back in. And then we say we're done. And then we exit down here. Insert does the same thing. We acquire the lock. We do the insertion to the beginning and the end, and then we write some as we're doing, then we release the lock. So when you run this, this is what you see. Well, that's the wrong thing. Reader-writer example. All right, this is what you see. So a read begins, it ends. A write begins, it ends. A read begins and ends. A write begins and ends. So it's just one after the other. Maybe read, 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 then a write, then a write, then a read, then a read, then a write. But you never have two things going on at the same time. It's completely sequential. One task finishes before the next one gets the lock and gets in and does its thing. So, would it be safe to have multiple write methods running at the same time? To have two tasks simultaneously trying to add to the beginning and end of the list. That doesn't sound like a good idea. In fact, let me show you what happens if you do that. So I'm going to go and I'm going to comment out. Oops. I'm going to comment out. I'm going to comment out the synchronization. And I'm going to to be using big numbers, so I'm going to get rid of these right lines. I'm going to take out the delay, or it will take forever. I'm going to do this. I don't want to write anything out because it takes too long. I'm going to get rid of the synchronization. And then I'm going to come up here and up this to like 5,000 times, no, 3 times limit. That's what I want. I got to change limit. I'll change it to 10,000. So we're running this with no synchronization at all. So we're going to have multiple threads reading and writing lists, the same list at the same time. And there's going to be like 30,000 of them. Right away it crashed. Normally it takes longer. So it's saying here, one or more errors occurred. Yeah, I'm not sure exactly what happened. If you run it again, okay, what's going wrong? What's causing the exception? It says index was outside bounds of the array. Why did that happen? Just from removing the locks. Yeah?
Are they both trying to write to the same index at the same time?
Yeah, something like that. One, they're both being they're both modifying the list at the same time, and somehow it, they interfered with each other in such a way that the list got corrupted. Okay, the lists aren't designed to be modified simultaneously. All right, so we need to do some form of locking, but the kind of locking we're doing is too draconian. We don't want to have 2 writes going on at the same time. Let me get back where we were. Can we have 2 reads going on at the same time? Is there anything wrong with having one list object and 2 threads iterating over it at the same time and printing it out? Turns out there's not. It's safe to do simultaneous reads on a list in C# and .NET. It's not safe to do simultaneous writes. So what we need is a more flexible locking scheme that allows multiple readers at the same time. So if I got a task comes along and wants to read, okay, it starts reading. The next task comes around and wants to read, it gets to read. It doesn't have to wait for the other one. As long as it's reads coming in, they're not blocked. But then a write request comes along. It's going to have to wait for all the readers that are currently running to finish before it can start. In the meantime, other readers have arrived and they're being blocked out because there's a writer ahead in line. As soon as that writer finishes, then the readers can proceed again. So multiple reads at a time, but only one write at a time. So there is a lock provided by .NET. It's called Reader-Writer Lock Slim. There's one called Reader-Writer Lock. I think Slim is just more efficient or something. I'm not sure why they named it that. We're going to use it. So let's go to the code here. So instead of using a monitor, I'm going to, there's a method called Enter-Read Lock on that Reader-Writer Lock Slim. And then there's a method called Exit Read Lock. There's a method called Enter-Write Lock, and a method called Exit Write Lock. So when we want to read it, we acquire a read lock. When we want to write it, we acquire a write lock. And now when I run it, let's see what happens. Okay, so you notice like read 6 and read 1 were running at the same time. Read 3 and read 0. Okay, and what you're seeing printed out is the readers print out the lists. So if you went back and studied it, you'd find that, look, a bunch of reads were happening simultaneously here. But there's a write right here, and nothing else happened between the write beginning and the write ending. no readers were allowed to run, no other writers were allowed to run. So we have the simultaneous readers happening, but anytime a write came along, it's just one at a time. So that's what those locks provide for you, that solution to the reader-writer problem. Now, what I want to do is make a homemade reader-writer lock. How do you suppose we do that? What do we use as our primitive, our material for making a homemade reader-writer lock? Yeah?
We need a queue and a mutex.
Well, you said we need a queue and a mutex. A mutex is another kind of low-level synchronization. I'm just going to use the low-level ones we've seen today. Yeah? Two booleans. Okay. You have to be careful about making sure things are atomic. All right, let me show you my solution. So I told you, your PSA is going to be something on the same level of complexity as this thing we're about to look at, my homemade, my read-write lock. Okay, so here's my first attempt at a read-write lock. So I have a sync object I'm going to use for locking, and I have a reader count. The reader count tells me how many readers are currently hold a read lock. Okay, so let's look at enter read lock. We'll look at enter write lock first. So a write lock comes, to get a write lock we have to, no, this is just a constructor. I'm just creating the object and saying the reader count is 0. All right, read lock comes along and it acquires the lock, the sync lock, long enough to increment the reader count. And then it releases the lock. Okay, but it has to get that lock first. Now look at enter write lock. What happens there? Let's make sure you can see both things. So the reader has to acquire the lock just long enough to increment the reader count, and then it releases the lock. What does enter write lock do? Yeah?
Does it wait until reader count is...
Well, yeah, that's what that does. What's happening here?
It's just acquiring.
So it's acquiring the lock, and then it is not releasing it. So ignore this for a second. The difference is the reader acquires the lock, increments reader count, and releases the lock. So another reader can come along, acquire the lock, increment the reader count, release the lock. So any number of readers can come in here. They briefly have to wait while this thing is being incremented. But they can go on and do their business until, and there's no lock being held until we exit the read lock. A write lock's different. Once it obtains that lock, it does not release it until we exit the lock. That's when it's released. Now, what is that? You can probably figure out what it does just from the name of the method. Yeah?
Basically just waits until all the readers are done.
Right. It busy waits until the reader count goes to 0. So the idea is the writer is going to come along, it's going to obtain this lock. Now that's going to prevent any new readers from getting this lock up here. So any incoming readers that are trying to get an enter read lock are going to be blocked. Meanwhile, so that it sits there. And so over time, the existing read locks are released one after the other as they complete, and the reader count goes down to 0. At that point, this busy loop ends, and now we have the write lock. Then, eventually, to exit the write lock, we just release the lock on sync. So this is where it was important that we acquire the lock here, we release it down here. They need to be in separate places. To exit a read lock, all you do is decrement the reader count. So there's my homemade reader-writer lock. Yeah?
I'm confused why sync is just an object type, like you assigned it to an object.
To acquire a lock, you just need to have an object to place the lock on.
Just anything.
Yeah.
Is fine.
Yeah, anything's fine. as long as no one else is using it for that purpose. Okay? So, I sort of resisted looking up how to do this, and it could easily contain mistakes, and it took me a while. Like I said, it's different from the kind of programming I typically do. But it just makes creative use of locks on this thing. Readers get a temporary lock just long enough to increment reader count, and that'll block out all writers until reader count goes back to 0. Well, the write lock, though, is obtained by holding onto that the lock on the sync object and not letting go until much later when we exit the write lock. Yeah?
So why a spin weight versus some other?
Okay. So he's asking why spin weight instead of something else. All right. In fact, that's an issue. I don't like spin weights because that's just using a whole task. And there is actually another implementation of this, I may have time to show you, that uses reset events, uses signaling instead of spin weighting. But we're not quite there yet. So this is all, it's hard to think about. Think back to when you were learning to program, and you sort of had to get used to, in your head, being able to look at some code and say, okay, the computers do this, and then that, and then that, and then it's going to repeat. And 1410 students have a really hard time with that, some of them. Just visualizing or imagining what the computer's doing with the code. It's like learning that all over again here, because you've got to imagine how could different threads interfere with each other. Is it possible there's a race condition where sometimes, in a rare case, one thread will get past another? So it's important to be able to test these things. So how would you test these locks? How would you test a my Readwrite Lock 1? How would you write a unit test for it? What would a unit test look like? Because that's what you'll be doing on PS8. You'll be implementing something like this and testing it. Yeah?
Do you just have a read write to a list, and then if a list throws an exception, then it's accessing or modifying it at the same time?
Okay, so yeah, we want to write code. We want to make sure that, for example, let's say we want to test whether multiple readers could be running at the same time. We have to have some way of knowing if they are running, right? We have to have some way of knowing if they've acquired the lock and are in the critical section. How can we find that out? How could suppose we let 10 threads loose and they're each supposed to acquire a read lock. How can we find out that they all simultaneously are executing inside the critical section? That's the key. So let's see the solution I came up with. So that is in the class Readwrite Lock tests. I just wrote one. Maybe we'll add another one here. All right, so what I'm going to do is create 100 threads, 100 tasks. And I'm going to have one of my read-write locks. I'm also going to create a manual reset event. I'm going to need that as part of the test. I'm going to have an array that contains all the tasks, and I am going to have a count that starts out at size. So let's see what happens. I spin up 100 tasks here, and they all call the reader method. Let's see what the reader method does. They acquire a lock, then this is the critical section, and then they release the lock. So I want to write some test code that can verify that all 100 tasks are in the critical section at the same time. So how do you suppose I can tell from the code that you see there? How can I tell, first of all, that all the tasks are currently executing inside the critical section at the same time? What is each of these reader tasks doing? What's happening here? Yeah? Okay, so we're atomically decrementing count. So there's a count variable that we are decrementing. And then we are waiting for a signal. Only after we receive the signal do we release the lock. So back to the test case. Here is, these 3 lines of code are the important parts. We wait. What are we waiting for? We have a spin wait here waiting for something to happen. What are we waiting for? When will that spin wait stop spinning? What's that delegate say? Right. We're spinning until count hits 0. Now we initialized count up here to 100. We created 100 tasks. Each task, first thing it does when it enters a critical section is it decrements count. So what does it mean when count reaches 0? It means that all 100 tasks have reached that decrement statement. Furthermore, none of those tasks could have proceeded out of the critical section yet because they're sitting there waiting for a signal, right? So when count reaches 0 and before we've sent the signal, we know that all 100 tasks are in the critical section where they're supposed to be. So they didn't block each other out. Okay? And after that happens, after we have seen the count go down to 0, and we know that we've verified that all are in the critical section, what's happening here? What's going to be the effect of calling mre.set? Right. All 100 threads are waiting on that MRE to be set. And we set, and they all then proceed to release their locks and terminate. And here we say, we assert, basically we wait all. We wait for all of them to finish before we go on. Now, this parameter here is a timeout. So if that's in milliseconds. So if 5 seconds passed and all 100 tasks haven't, and count hasn't gotten to 0, the test fails. And if 5 seconds pass and all 100 tasks haven't finished, the task fails. Okay, so for example, suppose that we never signaled. Well, let me do something different. Suppose we do this. Okay, so we never find out that the count never goes to 0. So if we run the test case over here, it'll take 5 seconds, and it'll finally notice that the count didn't go down to 0, and it'll fail for that reason. Okay, so that's what, when you write a test for a multi-threaded program, you have got to use multi-threaded concepts. Now, let's write a test and make sure that, let's say we want to spin up 50, or let's spin up half of our read tests. I've got to make this simpler. I'm going to make sure that only one writer at a time can run. So let's write a test case that creates a bunch of tasks that want to write and make sure they run one at a time. So how would we do that? I'm just going to copy this method, and we're going to adapt it to our purposes. I want you to really think about how to do that test. Test method 2. Size is 100. I don't know if we need a reset event or not, but we're going to create 100 tasks, except they're going to be called writer. We're simulating writers. We want to enter a write lock. We want to exit a write lock. How can we make sure that only one at a time gets to run? You got any proposals? Yeah?
Could you just wait for a little bit, like remove the set and then make sure it's 1, never increment it up more than like whatever number it's supposed to be?
Okay? So, yeah, so what we can do is, you wanted to add something?
Oh, I was just gonna say, could you put a lock around, the tasks at I?
Well, I think we need a lock here. Let's see what we got so far. We fire off 100 tasks, each are trying to run a writer. They're all going to try to get a write lock, only one of them is going to succeed. We need to find out that it's gotten in and that none other have. So what I propose we do is we're going to write a loop here. And each time through the loop, we're going to check that a writer is in the critical section. Okay, so how can I tell? So what we're going to have the writer do is decrement the count, and then it's going to wait for a signal to proceed. So what should we assert in this loop? What was that? Okay, so we better make, first. So this is what we're going to do. We're going to give the task some time. So I'll give it 1/4 of a second to get into the critical section, and then I'm going to assert. So that gives it time to decrement count. So I'm going to assert that I is equal to count. So I is going down each time we make an assertion. So the first writer is going to decrement to 99. The next writer is going to decrement to 98. So each time through the loop we see. And then we're going to tell that task. What was the method? Set. Then we're going to tell that task to proceed. That will release the lock, and the next one should be able to get in. So let's run it and see how I did. I know a mistake that I made. At least I don't believe this will succeed. Yeah. So test method 2 is failing. And the problem is it expected 99, it saw 100. Okay, I wasn't expecting that. What did I do wrong? I think maybe I got to wait longer than 1/4 of a second. So I'm going to wait 2 seconds to get all those tests set up and running. Because certainly I should have seen 99. Yeah. Wrong one. Expected 99, saw 100.
Is it maybe less than 100? Less than size, possibly?
Well, let's see. I've got initially count as size. I'm delaying. During that time, one of the tasks should have set count to, should have decremented count. And then we assert that they're equal. Let's put a breakpoint there. All right, so I got a task there. So it's got there. I'm back in, so yeah, I'm not getting a lot of information that way. Let's look at it. Okay, this was typical of my experience writing these programs, is getting a little confused about what was going on. So let's look again at what's happening. The writer is going to acquire the lock, it's going to decrement count, and then it's going to wait to be told to go on. So I is going to start out at 99, and count should be 99 at that point. Anyone see anything? The for loop declaration? Specifically what?
Int I equals size minus 1.
Yeah, so the idea is, so size is the 100. Size starts out, so I will start out at 99, which is what we expect the value of count to be after one writer has run. I can't send you off to spring break with a bug like this hanging. So, good chance to practice.
Well, if you just set it equal to count, set I equal to count and start, it should be 99 then. And I mean, it shouldn't change, but.
Yeah, no, it shouldn't. Let's set the breakpoint there and run the thing. Okay, so we got here, I is 99, like I wanted. Count is,
Do you have the decrement count one since we decremented the size one?
count is being decremented down here. But the interesting thing now, count is 0. Oh, wait. Yeah. Oh, it's okay. Wait. Maybe the thing I thought would happen is happening. So I'll do this, and if it doesn't work, I'll let you go. One way or the other, you get to leave. Let me end this. We're using a manual reset event. And a manual reset event, the problem is once it gets set, it needs to be reset, or other tasks will be able to proceed. So I'm going to change it to auto reset event. An auto reset event, once it only lets really one task get through at a time. Then it resets, and then there has to be another call to set. So I'll try that and see if that's the problem. And otherwise, you'll just have to wait and find out. Okay. I'll figure it out before I post it. Have a good break.